Convergence of document and relational databases. Most relational database systems other than MySQL have supported XML since the mid-2000s. This includes functions to make local modifications to XML documents and the ability to index and query inside XML documents, which allow applications to use data models very similar to what they would do when using a document database. So a relational model, for the exception of MySQL supported XML, that allows them to make local modification to XML documents and the ability to index and query XML documents so that they can mimic what they would do in document database. PostgreSQL since version 9.3, MySQL since version 5.7, and IBM DB2 since version 10.5 also have a similar level of support for JSON documents. They also support JSON documents even though they are relational model. Given the popularity of JSON for web APIs, it is likely that other relational databases will follow in their footsteps and add JSON support. On document database side, Rethink DB supports relational light joins in its query language. So for document database model, Rethink DB supports join, kind of like a relational database. And some MongoDB drivers automatically resolve database reference, effectively performing a client-side join. Although this is likely to be slower than a join performed in the database since it requires additional network round trips and is less optimized. It requires a network round trip because it's outside compared to a relational database join. It seems that relational and document databases are becoming more similar over time, and that is a good thing. The data models complement each other. If a database is able to handle document-like data and also perform relational queries on it, application can use the combination of features that best fits their need. So if they both support these strengths and weakness, application or developer can better choose from them. Query languages for data. When the relational model was introduced, it included a new way of querying data. SQL is a declarative query language, whereas IMS and Codasil query the database using imperative code. Many commonly used programming languages are imperative. For example, if you have a list of animal species, you might write something like this to return only the shark in the list. Function get sharks inside var shark equal for loop, and then inside the for loop if, then return shark. In the relational algebra, you would instead write sharks equal theta family equal sharks parameter family, where theta, the Greek letter sigma, is the selection operator, returning only those animals that match the condition family equal sharks. When SQL was defined, it followed the structure of the relational algebra fairly closely. Select asterisk from animals where family equal code shark semicolon. That's where the relational database came from, or it follows the same algebraic expression. An imperative language tells the computer to perform certain operations in certain order. You can imagine stepping through the code line by line, evaluating conditions, updating variables, and deciding whether to go around the loop one more time. In a declarative query language like SQL or relational algebra, you just specify the pattern of the data you want, what conditions the result must meet, and how you want the data to be transformed, i.e. sorted, grouped, and aggregated, but not how to achieve that goal. It is up to the database system's query optimizer to decide which indexes and which join methods to use, and in which order to execute various parts of the query. A declarative query language is attractive because it is typically more concise and easier to work with than an imperative API. But more importantly, it also hides implementation details of the database engine, which makes it possible for the database system to introduce performance improvements without requiring any changes to queries. So later we will discuss this further in the ins and outs of storage internals. These are actually hide. These implementation were hidden in relational database language like SQL. For example, in the imperative code shown at the beginning of this section, the list of animals appear in a particular order. If the database wants to reclaim unused disk space behind the scenes, it might need to remove records around, changing the order in which the animal appeared. Can the database do that safely without breaking queries? Function get sharks. So these are the example we showed earlier. The SQL example doesn't guarantee any particular ordering, and so it doesn't mind if the order changes. But if the query is written as imperative code, the database can never be sure whether the code is relying on the ordering or not. The fact that SQL is more limited in functionality gives the database much more room for automatic optimizations. Finally, declarative languages often lend themselves to parallel executions. Today's CPU are getting faster by adding more cores, not by running at significantly higher clock speeds than before. Imperative code is very hard to parallelize across multiple cores and multiple machines because it specifies instructions that must be performed in a particular order. So because the SQL doesn't care about particular ordering, it's more forgiving when it comes to distributed database, particularly when handling large data. For imperative code, it's not so because you need to be careful of the particular ordering, and one function could be connected or could be stored from another function that affects the real-time dependency of these functions. Declarative queries on the web. The advantage of declarative queries language are not limited to just database. To illustrate the point, let's compare declarative and imperative approach in a completely different environment. A web browser. Say you have a website about animals in the ocean. The user is currently viewing the page on sharks, so you must mark the navigation item shark as currently selected like this. First, the selected item is marked with the CSS class selected. Second, the P or paragraph sharks is the title of the current selected page. Now, if you want the title of the currently selected page to have a blue background so that it is visually highlighted, this is easy using declarative language or CSS, like lee.selected greater than P, then inside semi-curly bracket background dash color, colon blue. Here, the CSS selector lee selected P declares the pattern of elements to which we want to apply the blue style, namely all P elements whose direct parents is an lee element with the CSS class of selected. The element P sharks in the example matches this pattern, but P whales P does not match because its lee parent lacks class selected. If you were using XSL instead of CSS, you could do something similar. XSL colon template match equal code lee at class equal code selected slash P. Next line, 4 colon blank, etc. Here the XPath expression lee at class equal code selected slash P is equivalent to the CSS selected or lee that selected greater than P in the previous example. What CSS and XSL have in common is that they are both declarative languages for specifying the styling of a document. Imagine what would be like if you had to use an imperative approach. In JavaScript, using the core document object model API, the result might look something like this. var lee elements equal document that get element by tag name quote lee, and for var I equals the one semicolon I less than lee elements that link semicolon I plus plus inside this is if lee elements I dot class name equal code selected open semi-curly bracket and var children. We discussed that in the previous chapter. So we have for if nested loops. This JavaScript imperatively sets the element chunks to have a blue background, but the code is awful. Not only is it much longer and harder to understand than CSS and XSL equivalent, but it also has some serious problems. If the selected class is removed, i.e. because the user clicks a different page, the blue color won't be removed, even if the code is rerun, and so the item will remain highlighted until the entire page is reloaded. With CSS, the browser automatically detects when the lead that's selected greater than p rule no longer applies and removes the blue background as soon as the selected class is removed. If you want to take advantage of a new API such as document that get element by, class name code selected, or even document that evaluate, which may improve performance, you have to rewrite the code. On the other hand, browser vendors can improve the performance of CSS and XPath without breaking compatibility. In a web browser, using declarative CSS styling is much better than manipulating styles imperatively in JavaScript. Similarly, in databases, declarative query language like SQL turn out to be much better than imperative query APIs. So, in databases, a declarative is actually much better than imperative query APIs, much like the styling in web browser. MapReduce querying. So these are the third type of querying. MapReduce is a programming model for processing large amounts of data in bulk across many machines, popularized by Google. A limited form of MapReduce is supported by some NoSQL data stores, including MongoDB and CouchDB. So some part of MongoDB actually use MapReduce as a mechanism for performing read-only queries across many documents. MapReduce in general is described in more detail in Chapter 10. For now, we'll just briefly discuss MongoDB's use of the model. MapReduce is neither a declarative query language nor a fully imperative query API, but somewhere in between. The logic of the query is expressed with snippets of code, which are called repeatedly by the processing framework. It is based on the map, also known as collect, and reduce, also known as fold or inject functions that exist in many functional programming languages. So in Python, you can also do a functional programming. So this map or collect and reduce, also known as fold or inject, kind of mimic those. To give an example, imagine you're a marine biologist and you add an observation record to your database every time you see animals in the ocean. Now you want to generate reports saying how many sharks you have sighted per month in PostgreSQL. You might express that query like this: select date underscore trump parameter argument month comma parameter observation timestamp as observation underscore month comma the next line sum parameter num underscore animals as total underscore animals. Next line from observations. Next line where family equal code sharks. Next line group by observation underscore month. The date underscore trump month comma timestamp function determines the calendar month containing timestamp and returns another timestamp representing the beginning of that month. In other words, it runs a timestamp down to the nearest month. This query first filters the observation to only shows species in the shark's family, then groups the observation by the calendar month in which they occurred, and finally adds up the number of animals seen in all observations in the month. The same can be expressed with MongoDB's MapReduce feature as follows: db.observations.MapReduce inside this function map, then double var year environment, and then function reduce with parameter key comma values next line. Inside this return array that's parameter values. Then open semi-curly bracket query colon open semi-curly bracket family colon code sharks next line out colon monthly shark report and closing. The filter to consider first the filter to consider only shark species can be specified declaratively. This is a MongoDB specific extension to MapReduce. Second, the JavaScript function map is called once for every document that matches query, with this set to the document object. Third, the map function emits a key, a string consisting of a year and a month, such as 2013-12 or 2014-1, and a value, the number of animals in that observation. Fourth, the key value pairs emitted by map are grouped by key. For all key value pairs with the same key, i.e. the same month and year, the reduce function is called once. The reduce function adds up the number of animals from all observations in a particular month. The final output is written to the collection monthly shark report. For example, say the observations collection contain these two documents: observation timestamp colon date that parse month, comma 25 1995, next line family colon sharks, next line species colon etc. So these are key value pairs object and then observation timestamp. The function map would be called once for each document, which results in emitting 1995-12, 3 and emit 1995-12, 4. Subsequently, the reduce function would be called with reduce 1995-12, 3, 4, returning 7. The map and reduce functions are somewhat restricted in what they are allowed to do. They must be pure functions, which mean they only use the data that is passed to them as input. They cannot perform additional database query, and they must not have any side effects. These restrictions allow the database to run the functions anywhere, in any order, and rerun them on failure. However, they are nevertheless powerful. They can parse strings, call library functions, perform calculations, and more. MapReduce is a fairly low-level programming model for distributed execution of a cluster of machines. Higher-level query language like SQL can be implemented as a pipeline of MapReduce operations, but there are also many distributed implementations of SQL that don't use MapReduce. Note that there is nothing in SQL that constrains it to running on a single machine, and MapReduce doesn't have monopoly on distributed query execution. Being able to use JavaScript code in the middle of a query is a great feature for advanced queries, but it's not limited to MapReduce. Some SQL database can be executed with JavaScript functions too. A usability problem with MapReduce is that you have to write two carefully coordinated JavaScript functions, which is often harder than writing a single query. Moreover, a declarative query language offers more opportunity for a query optimizer to improve the performance of a query. For these reasons, MongoDB 2.2 added support for declarative query language called the aggregation pipeline. In this language, the same shark counting query looks like this: db.observation.aggregate. Inside this key value of match family sharks, and then group ID year, month, total animals. The aggregation pipeline language is similar in expressiveness to a subset of SQL, but it uses a JSON-based syntax rather than SQL's English sentence style syntax. The difference is perhaps a matter of taste. The moral of the story is that a NoSQL system may find itself accidentally reinventing SQL, albeit in disguise.